everybody, welcome back to Measure Theoretic Probability. We have been talking about random variables and random vectors, and which are just vector valued random variables, and the sigma fields generated by both and some relationships between them. And I have been promising you we are going to get to talk about convergence of sequences of random variables. We are going to barely dip our toe into that water at the end today, but the next two videos, totally convergence of sequences of random variables. Today, I have to tie up some loose ends and prove a theorem from last time that we left unproven. So a random variable, let's talk about a one-dimensional random variable first. I have a probability space consisting of a non-empty set omega, a sigma field curly f, and a probability measure p. And then I have the real numbers equipped with the most popular sigma field for the real numbers, which are the Borel sets. And if you want to measure, then let's use Lebesgue measure, which corresponds to length. And what I'm going to talk about today, I actually don't need either measure. A random variable x is a function that takes in points in omega and spits out real numbers, and it needs to be measurable. This measurability condition says that if you take any Borel set over here and pull it back under x, that is, figure out the omegas that under the function x mapped into that set. The set back over here, that pullback set, that inverse image, needs to be in the sigma field on this space, the curly f. That is the measurability condition. For a vector valued random variable, we might also call it x, but it would consist of k components, capital X1 through capital Xk. And this is going to be a function that takes in points in omega and returns points in Rk, the k-dimensional reals. We can think of this as like x of omega equaling x1 of omega, x2 of omega out through xk of omega. And once you put those omegas in there, x1 of omega out through xk of omega is just a k-dimensional real number. The relevant spaces here are, as I said, an omega and a curly f, and the k-dimensional reals, and the Borel sets on the k-dimensional reals. We talked a lot about that last time, about Borel sets for higher dimensional spaces. We need this vector-valued random variable to be a measurable function, which means we need to take any Borel set over here in Rk and figure out which omegas map there under all those k components. And if that inverse image is in the sigma field curly f, then we have a measurable function if this holds for every k-dimensional Borel set. We did, in fact, prove last time that a vector-valued random variable is, you know what? We don't even need random variables for this statement. A vector-valued function is measurable if and only if its components are. So in this case, a random vector is valid because the words random vector already include measurability, if and only if the individual components are random variables. The sigma field generated by x, which is this vector valued thing, is the sigma field generated by this vector. Note that I have the sigma field parentheses and the vector parentheses here. I'm going to stop doing this after today, but I want to talk about it one more time. This is defined to be the smallest sigma field with respect to which x is measurable. Again, measurability says that if we take a Borel set and pull it back under x, pull back all the components, we get something in omega. That set must be in curly f, no matter what Borel set we choose from the space over here. In the last video, we saw a different kind of notation. We were always talking about k equals 2, but we talked about sigma of the vector with parentheses around it, and then sigma of just the x1 through xk. These are the same thing. A lot of people don't even know they're different things and don't distinguish them at all. And after today, I'm going to stop distinguishing them and saying this. But for the record, if we only have one set of parentheses, this is defined to be the smallest sigma field with respect to which each individual component is measurable. That means that if you look at the inverse image of a one-dimensional Borel set and pull it back under one component of this function, you need to get a set of omegas that form a set in the sigma field curly f. We did prove this in the simple case, and I'm going to omit the proof here. It's similar. It's not exactly the same. I'm not saying it's exactly the same, so look at it. But I have a lot of proofs, a lot of theorems and statements today that are k-dimensional counterparts to things we've done, and I've chosen to prove some of them and not others. But let me know in the comments below if you really want to see this proof. I have a theorem for you that characterizes what this sigma field generated by x looks like. I did state this theorem in the last video in the one-dimensional case, but didn't prove it because I was waiting for this. I was waiting for us to have it in the k-dimensional case. And if we can prove this theorem, we can take k equals 1 and we have the other theorem proven. So I'm going to start with a k-dimensional random vector x consisting of components x1 through xk. Part 1 of this theorem says that the sigma field generated by x, or by x1 through xk, consists of all inverse images of Borel sets from Rk. We did just say a few times that if I take a Borel set from Rk and pull it back under the vector x, that I need to have that result be in curly f. But what we don't know is that enough to define the sigma field over here generated by x? Shouldn't I throw in complements or countable unions, things like that? It's going to turn out that that stuff is already taken care of, basically by complements of Borel sets being complements and pulling back, or unions of Borel sets being unions and pulling back. So we already knew that the inverse image of any Borel set needs to be in this sigma of x. That's how it's defined. And we're going to find out now that that's all we need to pull back. We're not going to need to fill that out and turn it into a sigma field. We also have part double I of this theorem, which we had in the one-dimensional case, and it says that a random variable y, so I've got a probability space, an omega, curly f, and a p. I can talk about measurability of a random variable y and pull back Borel sets. For now, y is just a one-dimensional thing. So if I pull back a one-dimensional Borel set, that needs to be in curly f. That's how it's a random variable. But that's measurability with respect to curly f. I claim that y is measurable with respect to the sigma field generated by the vector-valued random variable x. If and only if y can be written as f of x for some measurable function f from Rk to R. We're now going to prove part I. I have to put off double I to a later date because I really need what's coming up, that is sequences of random variables converging to something. This proof is going to be like a lot of proofs you may have seen in another kind of analysis course, where you first prove it in like a simple case, and then you have a more complicated kind of function, but you say, I can write it as a limit of the simple ones. And so I need to be able to talk about those limits. So for now, we're just going to prove I. I'm going to start off this proof as I usually do by defining a collection of sets, curly M, which is a class or collection of sets, and it's going to consist of all subsets of omega that actually come from pulling back some Borel set in Rk. I really love to use this full notation here because it really tells you what's going on, but we're also going to be using abbreviated notation. We can just write this as x inverse of b, or x1 through xk inverse of b, or even like an open bracket, capital X is in b, close bracket, and there's other ways to write this. I usually like to pick something and stay consistent, but I do think it's really important that we become flexible here and be able to move between these kinds of things seamlessly. So we're going to get practice starting now. Part I of this theorem claimed that this is how you get the sets in sigma of x. And so what we want to do is show that curly M is equal to sigma of x. Since x is a random vector, we already know that the inverse image of any Borel set from Rk is in sigma of x. But the question is that a sigma field, or do we have to throw more things in? If we don't have to throw more things in, then it's defined just as we define curly M. So at this point, we might have to throw things in. We're not sure. The collection M is just pulling back Borel sets and not filling anything in. The collection sigma of x is pulling back Borel sets and potentially adding more things. So curly M is necessarily a subset of the sigma field generated by x, because that's just curly M with potentially more things thrown in to close it under complements and things like that. Note that curly M is a sigma field on omega. This is our typical show I, double I, and triple I. Sometimes I do all this, sometimes I skip it because we do it all the time. I'm going to split the difference here and just look at double I. I want to show that it's closed under complements. So I'm going to take any set A in curly M. Given how curly M is defined, A must be the inverse image of some set B. That is, A must be all omegas such that x of omega goes into B. And x is a k-dimensional function. So This B is going to be a Borel set in RK. This is how curly M was defined. And I want to show that A complement is also in curly M. So imagine a space omega and a space RK, and maybe I have a set A over in omega. And because A comes from M, we necessarily know that it comes from pulling back a Borel set in RK. So I'm going to denote that Borel set by this blue set here. And so the inverse image of these points form A. That's everything in A because they formed A. That's how A was defined, as an inverse image of a Borel set. This means every point in A maps into B. Not every point in B needs to be covered because a random variable does not need to be like onto the second space. But every point in A maps into B. And every point outside of A maps outside of B. Because if a point outside of A mapped into B, A was defined to be the inverse image of B. So that point would actually be in A. All of this is to say that the complement of A over here in the probability space is the set of omegas such that the function x maps them into B complement. B is a Borel set on RK, and therefore B complement is a Borel set on RK because it's a sigma field and closed under complements. And this means that A complement is of the correct form to be included in the collection curly M, i.e. A is in curly M. So it's closed under complements, and that's 1 out of 3 things you need to show to have that it is a sigma field. I'll leave the others to you. Note that each xi is measurable with respect to curly M. To show this, take any one-dimensional Borel set in R, so like one of the k-dimensional axes over here. Take a one-dimensional Borel set B. The inverse image under xi are supposed to be the omegas that are mapped under the ith component into that set B. If I'm just looking at where the ith component is going, I really don't care where the other components are going. This is the same thing as the inverse image under the entire vector valued random variable of R cross R cross R, eventually cross B, cross R, and all the R's. So I've got a lot of R's here. I've got K of them, and 1 B in the ith position. Again, the things that map into the set B, which is in the ith coordinate plane over here, are the things that map into the space for which the ith coordinate is in B. Curly M was defined to be all sets of the form X inverse of Borel sets. So is this a Borel set on RK? If it is, we are done with at least showing this claim. So it is a Borel set on RK, and here's why. If you look at this cross product of sets, this is R cross R cross R, etc., but the ith component is B. This is an element of the one-dimensional Borel sets crossed with the one-dimensional Borel sets crossed with the one-dimensional Borel sets, etc. Over here, I have a set in k dimensions. Over here, I have k different collections of sets. This is in here, which means this is necessarily in the sigma field generated by this thing, because the sigma field is going to start with these as base sets and build up from there. But last time we showed that the sigma field generated by the cross product of one-dimensional Borel sets is the Borel sets on RK, in this case, because we have k dimensions. So in conclusion, this xi inverse of B is this x inverse of all of this stuff. And because all of this stuff is in the Borel sets on RK, by definition, this, and therefore this, is in curly M, and that's what we wanted to show. As a recap, curly M is a sigma field for which each xi is measurable, and curly M is a subset of sigma of x. But sigma of x is supposed to be the smallest sigma field for which each xi is measurable, and M is contained in this sigma field generated by x, and that forces curly M to actually equal the sigma field generated by x, which is what we were trying to show. Let's now relate the sigma field generated by x1 through xk, or by x, where x is a k-dimensional vector, to the individual sigma fields generated by the xi. I claim that the sigma field generated by x1 through xk is the sigma field generated by the union of the individual sigma fields. I'm just going to prove this for k equals 2. Formally, you would use an inductive argument, but informally, if you can prove it for 2, you can prove it for 3, because if the union of this and this is some quality, the union of all 3 things would be that, and the union of, 2 things, it's induction. You know what I mean? So let's show it when k equals 2. I want to show that the sigma field generated by x1, x2 is equal to the sigma field generated by the union of the individual generated sigma fields. That's a mouthful. I'm going to show this direction first. The most natural approach here would be to take a set in this collection of sets and show it's in here. Let me know if you can do that. It wasn't a fruitful approach for me, so I'm going to do something different. But I'd love to hear it if you got that to work. Instead, I'm going to take any Borel set B in R2. I'm going to look at its inverse image or pull it back under the mapping x1, x2. So I'm going to consider x1, x2 inverse of B, which is all the omegas over here that map into B. If the result is in this set here, then we're actually finished, because this is a sigma field, and over here, this is defined to be the smallest sigma field for which this happens. So yeah, all we need to do is show that a set of this form is in this collection of sets. Here's where it gets good. By the lemma in the last lesson, it is enough for us not to pull back every 2-dimensional Borel set, but to only pull back sets over here that generate 2-dimensional Borel sets. Remember, we had a lemma that said, if you have a sigma field over here that's generated by some collection, if you pull back the collection, the core of that sigma field, and you get something in the sigma field here, then necessarily anything from the generated sigma field will also be in a set from the sigma field here. In other words, again, I don't need to pull back 2-dimensional Borel sets. I can pull back generating sets, and we have many ways to generate 2-dimensional Borel sets. The 2 that come to mind first is we can pull back a set of the form A cross B, where A and B are 1-dimensional intervals, A1 to A2 and B1 to B2, because those rectangles, A1, A2 cross B1, B2, generate the 2-dimensional Borel sets. But we also know that the 2-dimensional Borel sets is the sigma field generated by the cross product of 1-dimensional Borel sets. And this means that I could, instead of pulling back rectangles or intervals, I could pull back Borel sets here. And if they fall into F, then the sigma field generated by those fall into F. And that sigma field is the Borel sets on R2. So I am going to choose to do this second one. And so let's do it. Let's take any A and B Borel sets, 1-dimensional Borel sets over here. Note that the inverse image under the x1, x2 map of A cross B, that consists of all the omegas over here, such that x1 of omega, comma x2 of omega falls in A cross B. Those really are all omegas over here that fall into A under x1 and fall into B under x2 at the same time. We need those 2 things to happen at once for the 2-dimensional point to fall in the right place. In other words, this set is the same as the set of omegas for which x1 of omega is in A, intersected with the set of omegas for which x2 of omega is in B. Another way to write this is x1 inverse of A intersected with x2 inverse of B. And yes, you can go directly from here to here. It's just if you're not comfortable with the notation, I'm trying to write out every little piece for a while. So that's what we did. This set, this is a set, and this is in the sigma field generated by x1, because A is a Borel set in R1, and the sigma field generated by x1 is characterized by inverse images of Borel sets. Similarly, this is in the sigma field generated by x2. So both of these are sets, and if I intersect them, I'm not sure where that is, but I can say it's in the sigma field generated by the union of these 2 sigma fields, because I have an inverse image of something that's in one collection of sets, and the inverse image of something else is in another collection of sets, and I'm throwing those into a big bucket of sets. And that might not be closed under intersections, but when I generated sigma field, it is, because we throw in all of those missing pieces. So this set is in that big bucket, and this set is in that big bucket. And by the very act of creating a sigma field over here, the intersection of these 2 sets is in the sigma field generated by the bucket sets. So this is what we wanted to show. And we are done with the straightforward direction of this proof, showing equality of two classes of sets. Let's go the other way. Let's show that this collection of sets is a subset of this collection of sets. To this end, I'm going to show that the sigma field generated by x1 is contained in the sigma field generated by the vector x1, x2, and I'm going to show the same thing for the sigma field generated by x2. Why is this going to get us what we want? Because if this is true, then the sigma field generated by x1 union with the sigma field generated by x2 is also contained in this sigma field. Why is that? This sigma field is a big collection of sets. This sigma field is some subcollection. This sigma field is some other subcollection. It doesn't have to be disjoint like I'm making it look, but two subcollections within the big collection. If you union these, you'll get a collection within the big collection. So that's all I'm saying here. And we are done, because the sigma field generated by the union of these two sigma fields is defined to be the smallest sigma field containing that inner collection. And this is a sigma field containing that collection. So the smallest sigma field containing that collection has to be contained in that bigger sigma field. We're not done with the proof. We're done with showing why showing this is going to get us what we want. So let's show this. I'm just going to show it for one of these. It's the same argument for the other one. Let's prove that the sigma field generated by x1 is contained in the sigma field generated by x1 and x2. Here I am going to do the straightforward approach. I'm going to take an element here and show it's in here. So let's take a set A in this sigma field. X1 is one-dimensional, and by today's theorem applied to one-dimensional random variables, we know that A is necessarily the inverse image under X1 of some one-dimensional Borel set. But I need to get this X1 stuff in terms of X1 and X2 stuff. And this isn't bad. Note that A is also the inverse image under the vector function x1 and x2 of that Borel set crossed with R. In other words, what omegas in here go over here into, if you just look at one dimension of that space, into a set B, it's everything over here that goes into B, comma, everything else, like B with any other real number in the second component. This is in the Borel sets on R2, simply because the Borel sets on R2 are generated by crossing Borel sets on R1 with Borel sets on R1. B is a Borel set on R1 by definition, and R is a Borel set on R1, R1 being R, because the Borel set is a sigma field and it has to contain the full omega, which is the R. So it's definitely in there. This is in BR and this is in BR. The cross product is in B of R squared, the Borel sets on the two-dimensional reals. Given what I said on the previous slide, the fact that this A can be written as the inverse image under this two-dimensional map of a Borel set in R2 is what we needed to show that A is in fact in the sigma field generated by x1 and x2. So we're done. And with that, we're ready to talk about limits of sequences of random variables. So suppose we have a sequence of random variables x1, x2, x3, etc. on a common probability space. We do need to be, for this to make sense, all the random variables to come from a common probability space where the pullbacks are in the common sigma field F. It's just not going to make sense otherwise. My question to you is, what does the limit as n goes to infinity of xn equals x mean? Probably this x is a random variable, but still, what does it mean? We know limits for numbers for sure, but random variables are not numbers. They are potential wannabe numbers. They are all over the place, scattered and random. And so how do you talk about them approaching anything? You really don't. You have to bring probability in some way that brings numbers into things. For example, one way to possibly talk about xn converging to x is to say, I'm going to say that happens if the expected value of xn converges to the expected value of x. We haven't talked about that yet in this class, so if you don't know what I'm talking about, don't worry about it. But if you do know what I'm talking about, the expected values here are real numbers, and we do know what it means to take the limit of a sequence of real numbers. Another way to turn the random variables into numbers that we can take limits of is to look at the probability that the distance between xn and x is greater than any epsilon you might want to choose. So pick a really small epsilon, and the probability that xn minus x, that distance, is greater than epsilon. As n gets large, the probability should go to 0 if xn is approaching x. This is known as convergence in probability, and I will define that and write that down next time. You don't need to know that. The entire point of me saying this stuff is this is two ways to imagine bringing numbers into the problem. Expected values and probabilities are numbers. And we know how to talk about limits of sequences of numbers. But the first form of convergence we're going to talk about is pretty exciting. If you've taken my courses, you probably haven't seen this yet. If you've taken like mathematical statistics, I think you've seen convergence in probability and convergence in distribution and maybe convergence in mean or mean squared. Again, don't worry if you don't know what I'm talking about. But I never get to talk about almost sure convergence because it needs measure theory. Before I do that, let me write this limit that I was just talking about, which represents convergence in probability. This is what you usually see in your mathematical statistics course, but we can expand this notation, and the probability that xn minus x is the distance between them is greater than epsilon is it's the probability measure of the sets of omegas for which that happens. So this is part of the statement of convergence in probability. And here it is in our measure theory setting, where it's really all about sets in omega. But this is something we'll talk about next time. Let me define for you almost sure convergence. We already talked about how it doesn't make sense to talk about the limit of xn going to x because they're not numbers and they're random and they're variable. But we could talk about the probability that the limit of the xn is equal to x. If this is 1, we get this type of convergence that's actually usually written out with the measure theory notation like this. We say that xn converges to x almost surely if the probability measure of the omegas for which the limit of the xn is equal to x. These are just real numbers in here, and we can make sense of this limit if and only if this probability is 1. What's happening here is we are taking all of the omegas over here and shooting them through each element of the sequence of random variables, and that's producing real numbers over here that are approaching something. And if that holds for all omega over here, or at least almost all, meaning everything except omegas on a set of probability measure 0, then that's how we define almost sure convergence, which is the same thing as almost everywhere convergence in a more general analysis or measure theory course not involving probability. If this happens, we write that xn, and then we have an arrow going to x, and we put as over the arrow for almost surely. And for the record, this is also called convergence with probability 1, which makes a lot of sense as well. Is showing convergence almost surely easy? I think we should do some examples. We've been doing a lot of theorems and theoretical stuff, so I definitely want to do some examples next time. But the first thing I'm going to do is give you an alternate way to show almost sure convergence that's equivalent to the definition we just had that may be easier to use. And once we have that technique, then we can look at a lot of examples of almost sure convergence. And then I will define convergence and probability, and we'll see that almost sure convergence is stronger than convergence in probability in the sense that if you have a sequence, xn, converging almost surely to a random variable x, then that sequence necessarily converges in probability, but not the other way around. So I hope to see you in the next one.